now pleased to introduce tonight's speaker, Dr. Maria Zuber. Dr. Zuber is chair of the National Science Board. She is the first woman to hold this position since its establishment in 1950. The National Science Board has oversight over the National Science Foundation and provides advice to the President's office and Congress about directions and support of basic research in the country. Maria is Vice President for Research at MIT, where she is also the E.A. Griswold Professor of Geophysics. She is a member of the National Academy of Sciences. Maria's research focuses on structure and tectonics of solid solar system objects. She specializes in using gravity and laser altimetry measurements to determine interior structure and evolution of these objects, and she has been involved in more than a half dozen NASA planetary missions aimed at mapping the Moon, Mars, and Mercury, as well as several asteroids. If you want to know more about his research, you're going to have to ask her, because I just read the words. She was principal investigator for the Gravity Recovery and Interior Laboratory, GRAIL, and as such became the first woman to lead a NASA spacecraft mission. She received her PhD in geophysics from Brown University. And Maria likes to hang out with movie stars, as the next slide shows. She seems infatuated with Mars and really enjoyed the movie The Martian, which starred Matt Damon, who was shown here with Maria. They're good buddies, and before he delivered a commencement address at MIT. Please join me in welcoming Maria Zuber to Chicago. Maria.
Yeah, so that was that picture was my biggest retweet ever. So the news office put out a tweet that said, first woman to lead a NASA space mission standing with astronaut Mark Watney. So. Okay, so let's start out to frame the situation. The energy challenge, okay. Global energy demand is projected to double. We dramatically need to reduce greenhouse gases. At the same time, while we're deploying clean, affordable, reliable energy solutions, okay. In order to keep the world economy moving, fossil fuels are going to be in the mix for the next several decades, okay? And we need a rational, pragmatic, accelerated plan to use fossil fuels just where we need them, okay, which is mainly the transportation sector. And also to be very cognizant about the needs of the developing world. Okay, so here is a plot of the most populous nations in the world, and in the years 2015 and 2050. And so in the filled arrows that are purple here, that is the current population of the country, and the purple ones indicate that the population is rising, and the filled yellow arrows are countries where the population is decreasing. So, so this is the current population in the US today, and the number beside it is the population in 2050. Okay, so in the United States, we're going to go from 320 million people to 390 million people, okay? Germany, Thailand, Russia, China are going to decrease, but look what's going on over here in India. India is going to go from 1.2 billion to 1.7 billion. So there are going to be a greater increase in India in the terms of the number of people by 2050, okay, than there will be people living in the United States in 2050, okay. And then look at Africa. 182 million in Nigeria going to 400 million. 99 million in Ethiopia going to 188 million people, okay. These people need energy. Okay. All right, so here is a plot of the annual per capita energy consumption, and on the ordinate here is something that's called the Human Development Index, which is measure that includes matters such as life expectancy, literacy, education, standards of living, and so it, they go into this index and they're very high, high, medium, and low. Okay, and so you can see here this in this human developing index, and this is a plot of per capita energy consumption in kilowatt hours down on the abscissa here. And so you can see here that the developing countries tend to have low human development indexes and low per capita electricity consumption, and more advanced countries are out here. Okay, people in these countries want to be like us. Okay, they want what we have in terms of their standard of living. And the way that what they have to do to get it is to expend energy. Okay, so let me, so we're just pointing out some of these here. They want to be like us. Okay, so here is some of quote from the literature that just indicates we're rather pessimistic that it's possible for low-income countries to develop without increasing their level of energy use, given the need for energy to drive gross domestic product growth. Energy is also embedded in the construction of infrastructure when affluence levels go beyond the satisfaction of basic needs. So all countries that have reached higher development levels in the past have used energy inputs like steel and cement. And so it's hardly plausible that this correlation will break, at least in the near future. So this is just a statement that in order to increase standard of living, to increase standard of living, we're going to need energy. Maybe turning off the, are we back? Okay. Maybe turning off the airport would prevent that from coming up. So. Okay, I'm filled with optimism now. Okay. All right, couple minutes on the science here, okay? So people who don't believe that the climate is human-induced climate change say that the climate has always been changing, okay? And it always has, okay? And here's the data. Okay, this is carbon dioxide levels in parts per million, and this is a part of a core, actually an ice core from Antarctica, and here this is data. Okay, this is incontrovertible. These are observations of carbon dioxide bubbles in ice cores, so it is a direct measure of CO2 that was captured from the atmosphere. And as you can see, there are variations here. In the interglacials, the carbon dioxide level is higher. In the last ice age, the CO2 level falls. And so as you can see here, this core actually goes back further than 800,000 years. And this cyclic variation of changes in CO2 that correlate, okay, with the ice ages, which are related to orbital and rotational variations of the Earth. There is no question about these data, okay. And then what you see here is at the dawn of the industrial age, the CO2 concentration in the atmosphere shoots up here, and at the current level, we've now exceeded 400 parts per million, and we are in uncharted waters, okay? Because over the time of recorded history, we have never had as much carbon dioxide in the atmosphere as we have now, okay? So some part of that carbon dioxide that's in the atmosphere is due to cyclic changes that are naturally in the Earth's climate, but the preponderance of the increase and the rapid rate that we're seeing today is mainly due to human contributions of CO2 in the atmosphere, okay? This is not debatable, okay? So as there's more CO2 in the atmosphere, CO2 is a greenhouse gas. It's not the only greenhouse gas. So we're going to have rising sea level. There will be ocean acidification, and there are going to be effects that we do not understand, okay? Because we have never in recorded history been in the situation that we are now. So things are going to happen that we don't know about. So the hottest years, the 10 hottest years are all since 1998. 2014 was the hottest year on record until we got to 2016, which just blew away the record, okay? And 2016 is going to beat this record, okay? So the hottest year on record for some time to come is probably going to be the year we're in, okay? And we need to start thinking seriously about what we're going to do about that. So let's talk about consequences, and let's talk about things that we don't understand. So what I've showed you so far, this is data, okay? The CO2 concentration, data. The temperature is data, okay? Those we can't argue about. Then there are simulations, okay? And climate models don't have the full physics of the Earth's climate because the Earth's climate is a complex system, and we don't understand the complicated interactions of this complex system. But this, I wanted to just show this plot. This is hurricane tracks this is from the National Center for Environmental Information, and this is, I want to focus here on the North Atlantic. So hurricanes form in the summer to cool the ocean in low latitudes. They start off the western coast of Africa. The tropical storms come across. The heating of the water causes condensation in the atmosphere. The storms grow. Some of them come up the east coast, and they typically take a right, okay? But we're losing sea ice, okay? We have a lot less sea ice in the Arctic than we used to, and that's changing the albedo of the Earth, okay? So areas that are bright and icy reflect more of the sun's radiation than ocean water, which is dark, okay? And so the Earth is absorbing more heat at these higher altitudes. And actually, you know, there are a lot of things in climate models that are really uncertain, but one thing that we really know how to calculate very well is winds, okay? And winds just come from pressure differences, which are easy to determine from temperature differences, okay? So there's a lot of uncertainty, but wind patterns are something that we know how to predict pretty darn well, okay? And the models indicate that with the loss of sea ice, the wind patterns in North America are going to change. And it's going to cause hurricanes, a lot more hurricanes, to not take a right when they come up the coast of the North Atlantic. More of them are going to go straight, and more of them are going to hit the northern eastern seaboard of the United States, okay? So in the last several years, we've had Irene and Sandy, okay? And that's two events where over a period of time we have had very few hurricanes that have hit the Middle Atlantic and New England. And actually, we can't prove that Irene and Sandy were associated with climate change, okay? Statistically, it's impossible to prove that. All we can say is that these models tell us that there are going to be more Irenes and Sandys, and they're going to be very expensive, okay? And so these changes are happening now. And and we need to think about what we're going to do about this. Okay, so the next issue, suppose we stopped emitting today. Okay, what is the issue here? Here's a plot of carbon dioxide, and here's this is as a function of time, and this is different peak levels of CO2, and so it turns out that the temperature increases that we get due to the greenhouse warming, they're largely irreversible for 1,000 years. Okay, and this is due to two things. It's due to the slow rate of that carbon. Excuse me. That carbon is taken out of the atmosphere, and also we have a very slow rate of heat exchange with the oceans. The oceans take out heat from the atmosphere, but the oceans are very massive, and it's a very slow process. And so, so why the sense of urgency? Okay, the sense of urgency is that the decisions that we make, or the decisions that we put off, okay, these are consequences that we're going to have to live with for 1,000 years. Okay, so if we stopped emitting now, we still wouldn't take that carbon dioxide out of the atmosphere for a long time. Okay, and so that is really the greatest matter of concern among scientists, is that these decisions now, we're making decisions that are going to affect our children and grandchildren and their great-grandchildren by our lack of action. Okay, so so we need to decarbonize our global energy system. Okay, so we need to decarbonize as much as possible those parts of the energy system for which we can get by without using fossil fuels. We're still going to need fossil fuels. We're going to need it in the transportation industry. We're going to, particularly the heavy part of the transportation industry, and we've got a real problem with the energy needs of the developing world. And so actually, my colleagues, and I was head of MIT's Earth Science Department for nearly 9 years, and they said, well, you shouldn't say that we ought to keep using fossil fuels. And the fact of the matter is, we can't shut down the world economy. We have to have a functioning world economy. So fossil fuels have to come into the mix, and so we need to figure out how to capture that carbon or get the carbon out of the atmosphere. We need those strategies, while in parallel we are developing low carbon or zero carbon energy systems. Okay, so so basically we need even for all of the people who are going to need energy, we're going to wind up using our fossil fuels. Okay, but the fossil fuel industries are they're diversifying. Some got into the game rather late, but they all understand what I'm telling you right now. Okay, so a variety of issues. So I'm going to talk I'm going to give you some samplings of things that we're thinking about at MIT, but also that many of you in your activities are also thinking about. So the utility of the future. Okay, we have a global grid. It's centralized. The technology is outdated. Most of it's 100 years old or more. There are regulatory deficiencies in it. Do we fix this and update this global grid? Okay, or do we decentralize the grid? Okay, and so there are examples going on of decentralized grids in the developing world where they don't have energy grids. Decentralized grids that work locally are a pretty favorable idea. Many of us are buying hybrid cars or electric cars, okay, and proudly thinking that we're decreasing our carbon footprint, okay. But if you want to think about whether or not you're really decreasing your carbon footprint, you've got to think about where the electricity to charge your car is coming from, okay. So this is a map of gasoline fuel economy, the equivalents in miles per gallon of an electric vehicle that's charged using the grid electricity mix in each grid in the region of the United States. Okay, so here to charge your car, okay, it's 43 miles per gallon is the equivalent of electricity that you use to charge your car. Okay, but hybrids that run exclusively on gasoline are 50 miles per gallon, 55 miles per gallon, 48 miles, so on the order of 48 miles per gallon. And what this diagram is actually showing us that electric vehicles that are charging on today's grid mix only have an emission benefit, okay, if in the lightest blue areas, okay. So if you live in the Midwest, you are not decreasing your carbon footprint by driving a hybrid car. Okay, so we've got to lose the coal plants. Okay, so let's look at some technologies. Okay, okay, all right. So batteries. Okay, storage is a big deal, and here are grid storage, different kinds of batteries and the shipments per year. And it shows you that lithium-ion is by far the biggest source of battery technology that's being deployed. You know, we have lead-acid flywheel flow batteries, various other kinds of batteries. Now, in making lithium-ion batteries, after 25 years of development, these batteries are still too expensive. Okay? And part of the reason for this is that in 25 years, we basically haven't changed the process that we've used to produce these batteries. Okay, we're still using the same manufacturing process, which goes through a whole variety of steps that takes a long time and is expensive. Okay. So at MIT, one of our professors, Yet-Ming Chang, has actually greatly simplified the manufacturing process for lithium-ion batteries. And in doing this, has gone from a traditional solid battery and combined a flow battery, which is has particles suspended in liquids within the battery. And he's mixed that together into a semi-solid battery, which actually can decrease the time of production by a factor of 2. So this is one way that that we're going to make lithium-ion batteries more affordable. Okay, there's a dropping cost of renewable generation, and the hope is that this is going to facilitate the integration of storage. So as renewables become cheaper, we'll be able to take better advantage of the storage. So this is cost, the levelized cost of electricity. You can make this for whatever your favorite electricity is as a function of time. And so for solar PV, it's actually has decreased. The price of PV has actually decreased by 85% since about 2006. So this technology, solar technology, is really becoming far more cost effective. But there's a baseload issue, okay? And here's the generation as a function of time over the period of a day. And this is well known. The sun shines in the day, and we get a lot of power that's generated, and then we don't have it at night. And so if people who have solar panels on their house, they have more energy than they need during the day, and they want to sell it back on the grid so other people can use it, but everybody else with solar panels on their grid is selling that back at the same time, and the grid can't handle it. Okay, so we can't take advantage of what we have unless we have longer lasting batteries. Okay, but there are issues on more than a daily basis. Here's the period of time over the course of a year. Here's the normalized PV power over the course of a year. And so it depends what time of year it is, but you can see the variation occurring over the course of a year as well. So we really need to be thinking not only about storage over a day, okay, but we need to be thinking about longer term storage as well. Okay, are there other kinds of batteries that we can use? Well, there's a lithium sulfide battery, and sulfur is it is an abundant element. It's very light, and like lithium, lithium is another light element, and lithium sulfide batteries and other batteries that with sodium sulfide. These have a high power density, and they're very lightweight. And if we look at the combined costs for different kinds of batteries, what you can see here, these batteries that contain sulfur in them are becoming much more cost effective. And so I think we're going to be seeing more of those in the future as well. More thoughts. So better batteries are going to enable seasonal storage. If you look at the amount of the solar insolation that we get and how that varies as a function of time. So here's the map of the United States. Over here is insolation in July. Over here in insolation in January, and here is the average insolation over the course of the year, and you can see relatively large differences that are latitude dependent, of course, and so again, more evidence that we need to think about seasonal storage. Okay, concentrated solar. Here's on demand. Okay, so here is a design of a system by Professor Alex Slocum, who's a mechanical engineering professor at MIT, where we put solar reflectors on a hillside and concentrate them in a particular area. So this is actually, if anybody remembers the James Bond movie, The Man with the Golden Gun, a very similar concept was proposed there. But here, the energy then is directed into a pool of molten salt and water so that it can be stored, okay? And so this can provide longer-term storage, and you can then put it back into the grid over much longer time scales. Okay, solar cells, okay? So there are, one of our professors, Vladimir Bolovic, has developed new solar cells that absorb sunlight only in the infrared and ultraviolet. Okay, visible light passes right through them. So this is a picture of the Hancock building in Boston. So you could essentially cover all the windows. It's all windows. You could essentially cover all the windows of the building with these solar cells, and it would provide 25% of all the energy that's needed for the building, okay? And but looking out the window, you wouldn't notice it because there's the sunlight just passes right through in the visible. And of course, this could be used for portable electronics as well. Okay, other ideas. Here, this is wind, using wind and using this for energy storage. So, so we've got wind energy being generated here, and the excess wind power from shore. We've got this sphere that is anchored down on the bottom of the ocean. And so, so when this is charging out, the wind power comes down, and the water level goes down in this, and then when we discharge, when the power is needed, it's sent back to shore, and the water level rises within the sphere. And we're just using the wind here and the water level adjustments to provide storage capabilities. There are designs from our nuclear science and engineering faculty on floating nuclear plants. And these could be put offshore. The size of them could be varied. They could be anchored to the ocean bottom. And the advantage of these is that so it's you've plenty of water for cooling purposes, and if there ever were a critical situation, you're surrounded by water, and that water could be let in but not released, so that it would actually is an increased safety feature. But we can actually do better than this, because there are designs of, I'm actually a very big proponent of advanced nuclear energy, okay? And there are many of my colleagues, and actually me, I think I would put myself on that list, who think that we can't really solve this problem without increased investment in nuclear power. And so we've got a nuclear reactor startup in Kendall Square. A couple of our alums have started it, and in this startup, the reactor, the fuel is not cladded. Okay, it's actually put in a salt bath, and the fuel in this is spent nuclear rods. Okay. So here you're solving two problems at the same time. You need clean energy, and you need to do something with the nuclear waste that we have. And so in this case, nuclear waste is the fuel. Okay, and because the fuel isn't surrounded by rods, you can continually remove the fissioned products, and in comparison to the current lightweight water reactors, so this reactor it's more compact, it's more affordable, it has a higher energy density, and it can't melt down. I mean, it's impossible for it to melt down. Okay, and so this actually has venture funding, and the business plan for this startup is that they're hoping to build a prototype by 2020, and this the idea is that they will build it for the cost of a coal plant, and it will produce as much power as a coal plant, but at zero carbon. Okay, so what's not to like about that? Okay. But the real game changer in all of this is fusion, and it's the fusion of hydrogen into helium, and we've got several of the reactions here: the deuterium-tritium and deuterium-deuterium, which occurs at very high temperatures and high pressures. Okay. A couple of months ago, this is the inside of a fusion device, a fusion experiment on the MIT campus, it was the last experiments that were run on this before the Department of Energy shut it down, because it's transferred the funding to a European advanced reactor. And this was the first fusion experiment anywhere that actually got above 2 atmospheres of pressure, okay? And in order for fusion to take place, you need some combination of very high temperatures and very high pressures, okay? And the experiment in France is called ITER, and it's the size of it is the better part of the size of a football field. Okay. However, there are now there's been a breakthrough in materials. There are now superconducting coils that allow much higher magnetic fields than previous superconductors. And so in order for the fusion reaction to take place, the plasma has to be contained, and has to be contained at high temperature and high pressure. And so in order to contain it and to keep increasing the pressure, you need very high magnetic fields, okay? And so the design that we are producing on our campus now actually will get to pressures that this experiment, the better size of a football field, will be producing in 2030 or so. It can actually be made to be about the size of this room, okay? Just because of the ability to have the higher magnetic fields to contain these experiments. And in addition, this experiment is it's fully modular, so it's easy to take it apart and replace parts. It is needed, as opposed to a very big experiment, which it would be down for months and months to years in order to make changes. Okay. So those are some of the technologies. I wanted to talk a little bit about partnerships, okay? And I'm a big fan of partnerships because it's going to take all of us working together to solve this problem. So MIT just joined in a partnership with the Boston Medical Center and the Post Office Square Redevelopment Corporation. And this is a place called Summit Farms in North Carolina, and it's 650 acres, and it's more than 4 times the size of the MIT campus. Okay, and so we're putting by the end of this year, there will be 255,000 solar panels on it, which will produce 60 megawatts of electricity. And this electricity will offset electricity in this area that's currently being produced by a coal plant. Okay, so it's going from dirty to very clean. And so we have entered into a power purchase agreement where we agreed before it was built to purchase the full 60 megawatts between us and our partners. So this will the offset of this energy will lower MIT's carbon footprint by 17%, and it will cause the Boston Medical Center and the Post Office Square Corporation to both be carbon neutral, okay? And neither of these organizations had the ability, in terms of the ability to explore it, negotiate it, implement it on their own. And we're happy to team with MIT, where we like to do things like that. And but in addition to lowering our campus, offsetting the carbon footprint of our campus, which is a very difficult thing to do for a place in the northeast, okay, or in the Midwest, where you don't have lots of sunlight and where you have cold winters. It just shows the value of partnerships, and we're so excited about this. We are exploring other kinds of partnerships with other kinds of clean energy. Okay, and I'll tell you, I'd love to do one with nuclear once we get our nuclear startup going. Okay. I just want to talk really quickly about policies, because being from MIT, I will tell you, all the great technology that we can conceive of will do us no good if we don't have the policies in place to allow those technologies to be deployed and implemented. Okay, so here, absent substantial greenhouse gas policies, the market's unlikely to lead to the phase out of fossil fuels on the time scale that we need this to happen. Okay, isn't going to happen unless there is an incentive to do so. And so we hear a lot about how we're running out of fossil fuels, and this is proven reserves. And so by proven reserves, we mean reserves that can be extracted at a market price. Okay, and so here's oil reserves, here's natural gas reserves, and it keeps going up, up, up. Okay, because while technology has contributed to advances in clean and renewable energy, it has also contributed towards the identification of new fossil fuel resources and being able to extract them economically. Okay, so technology has also benefited the fossil fuel industry, and so unless there are policies that really drive the incentivization of the clean energy, we're going to keep using fossil fuels. Okay, and like I said, we should be using fossil fuels for only what we can use no other energy source for. Okay, so last year at the UN Climate Conference, COP21, they announced the Breakthrough Coalition, where a number of developed world countries have pledged to attempt additional investments to try to get these clean energy technologies matured and deployed, and it's been a tough road to hoe to get this moving. Bill Gates is behind this, and in his opinion, there aren't enough ideas out there to actually fund if we had this kind of funding now. But the ideas are coming along. Okay, and so obviously this needs to happen. So I want to end on an optimistic note because I'm really an optimistic person, and so I end with a quote from my friend Piers Sellers, and Piers is the deputy head of Earth Sciences at the Goddard Space Flight Center, and he's a climate scientist, and he was also an astronaut who had several shuttle flights into space and observed the beauty of the Earth from orbit. And last November, Piers was diagnosed with stage 4 pancreatic cancer, and he made the decision then that he was going to use the time that he has left on this Earth in order to talk about how the steps that we need to take to address the threat of climate change. And here's what he said, and it's far more eloquent than anything that I could say on the matter. There's no convincing demonstrated reason to believe that our evolving future will be worse than our present, assuming careful management of the challenges and risks. History is replete with examples of humans getting out of tight spots. The winners tended to be realistic, pragmatic, and flexible. The losers were often in denial of the threat. And so, I just want to close by saying, right now, the goal is to limit warming of the Earth to 2 degrees. We're already at 0.8 degrees. And if anything, the temperature increases are exceeding the projections from nearly all climate models. And on the basis of where things stand today, we can't get there. Okay. So we need breakthroughs, and I happen to think that there are going to be breakthroughs. And so I just wanted to leave you with that thought that I'm optimistic about this, and we need technology, but we also need changes in human behavior. And in the near term, until these technologies are matured and deployed, increases in efficiency are going to be the biggest thing that we have to work with. And increases in efficiency is going to be one thing, but changes in human behavior and the way that all of us live our lives have to be part of the solution. And so every single one of us has a role to play in this. It's not something that can just be left to the scientists and technologists. And I'll stop there and be happy to take any questions.
Try to answer questions, whatever.
No guarantees. I can try.
Hi, Mohammed Shahiripur with IIT main campus. I have a couple of questions. One is that I felt that you left out a discussion on energy efficiency, in the sense that as population in India, China, all those places go up, rather than generating more, we need to educate people to turn their lights off, in the sense that we are wasting quite a bit of energy at this time, and there is no reason to move on in the direction that we are. That's one. The other one is, you pointed out that where are we going to get energy to charge all those cars? At this time, after midnight, we have so much excess energy available, and we cannot turn those power plants off because of their thermal constraints, that we basically turn the price of electricity, locational marginal prices, to negative. We pay people to use electricity. So that's the time to charge those
That's
cars.
right.
So really,
Absolutely.
we don't need any extra energy available to charge those cars. We already have energy available, we're just not using it efficiently.
Yeah, that's right. So I did allude to efficiency at the end. So yes, people need to turn off their lights, but there are people who don't have, a lot of electricity now. So in India, India has a lot of coal. Okay, and it's not only coal; it's lignite. So it's like the dirtiest coal. Only peat is dirtier, and so. Unless we can come up with deployable clean energy solutions that will work on local grids, India is going to burn their coal, okay, because their people need energy. But clearly, increases in efficiency are needed, and you're right. The time to do this charging is in the night when people aren't using electricity for other means. Yeah, right there. Yeah, it's pretty.
Just like I used to have a minivan, 20 miles per gallon. Now I have a Prius. Doesn't plug into the grid, so it doesn't matter what the grid. But the electricity is made here. I'm only using half the gas I was before.
Yeah, well, increases in. So if you had a big old Volkswagen bus and you went to a Prius, yes, but yeah. So. Well, you're charging up your Prius with
It's a hybrid thing, right? Prius hybrid, yeah.
Well, there are non-electric and electric hybrids.
Well,
Yeah.
it's not, anyway, it seems like you made the statement that the Priuses aren't helping us in the Midwest. And it seems to me like the non-plug-in hybrid is just a regular Prius hybrid or many other hybrids.
I'm talking about the ones that plug in.
It's an electric
Yeah.
vehicle.
The audiovisual team is telling me that we need to use the microphone for the recording, so I'll walk it around to the
Oh, that's right.
folks
It's
asking
being recorded,
questions.
so we need to use the mic. So. Oh, there's one back. Wait, we got one back there. We got a.
Okay, so can you guys hear me? Is it okay?
Yeah.
Okay, so science literacy is like really important, and I believe knowledge is power. So if you were to teach kids something, like I'm talking little kids, where would you start on teaching them on how to change your behaviors to help make the future better for energy?
So I think okay, well, we heard it from the mic. Okay, so the question is science literacy and how would you educate young people? So I think young people are not the problem here. Young people are getting with the program. And so today in Massachusetts, every ninth grader has to calculate their household carbon footprint. So if you go home, you have to calculate your household carbon footprint. It sends a powerful message to you. And let me tell you, you don't want to be the person in the class with the highest carbon footprint. That's it. In fact, my son came home to me when he calculated, and one of the things was, how many miles a year do you fly? Okay, and he came home and he said, Mom, you and some girl whose father goes to Asia, once a month, like, we're the worst. I mean, how could you do this? You're the head of Earth Sciences. So I then looked into offsetting my carbon footprint for flights. So I'm no longer a disaster. But young people are getting it, and they understand the efficiencies. But they've you can't say, oh, we've got to start burning fossil fuels, and then go back to your dorm or wherever and plug in your 6 electronic devices, right, and open the window. So there are behavioral changes that I think when groups get together. They tend to think pretty creatively about these, so it tends to be a little bit like a contest. But I think I think you could calculate your carbon you don't have to wait till 9th grade until you start doing that, because middle school you could easily do that calculation. So let's see, how about this guy right here? You? Yeah.
So I had a quick question about the solar panels in North Carolina. I was just wondering, what kind of materials are those going to be made out of, and what benefit does North Carolina actually get from that project?
Okay, so first of all, they had a, so that was I don't remember the particular kind of solar, but I can look that up right afterwards. But the benefit that North Carolina gets from that is this was a former tobacco field which was lying fallow and couldn't be farmed on. Okay, and so we signed a 25-year lease and agreed to buy all the electricity if this solar panel farm was built, and that our commitment to buy all the electricity that was generated at this solar farm allowed them to get the financing to build it. So it means jobs in North Carolina, and they're generating electricity that used to be generated by coal. So that there's multiple benefits to the state of North Carolina. I mean, we really looked into, ideally in our dreams, we thought about that we'd like to do this in New England, but there wasn't big enough tracts of land, there wasn't enough sunlight, and the energy generation in New England is a lot cleaner than it is in North Carolina. So we wound up just getting a whole lot more benefit. So after 25 years, if they wanted to go back and farm that land, then they could do it in principle. But I think we're just going to see a lot more of these in areas that have broken land. But there was actually a lot of benefit to North Carolina on this. Okay, let's get some over here. How about this guy right here? Wait, you have to stop because we're being recorded, so we need to hear your voice on the microphone.
Two questions that are interrelated. Thank goodness you're an optimist. But you said also that the technology can go almost wherever we want, but nothing's going to happen unless policy changes. And there's an elephant in the room. I mean that literally. So thank you for being an optimist. Many of us are not. And related to required policy changes, unless something's changed, some of your own colleagues are not helping on the policy front without mentioning names.
Okay, so let me just make a comment on that. Yes, I just returned from Marrakesh. I was at the UN climate conference, and there's a lot of uncertainty. But what I will say is both representing MIT and representing the National Science Board, that divisiveness in this country has been tearing us apart, and we will not contribute to further divisiveness. So I feel like we need to work together to solve this problem, and we are making ourselves available in an educational way and in any way that we can to move this situation to a better place. And we've had a setback, and it isn't going to be easy. But right now, this country has 250,000 jobs in solar energy and 50,000 jobs in coal. And I think that a president who commits to job creation is not going to want those 250,000 clean energy jobs to go away. And we're committed to work with the president on this. And there's work to do, but we're committed. What this guy right here?
My questions were relating to the carbon that's already in the atmosphere. Is there any work going on to removing carbon biologically through, bacteria use or?
Yeah, so actually MIT has
I have one more question too. Is also I noticed that you were mentioning your storm patterns, and most of the storm patterns are going to be hitting right at North Carolina, where you're building your power plant too.
Yeah, well, it's a ways in from the coast, thank goodness. So let's see, taking carbon out of the atmosphere. So MIT, we've actually we're joining a collaboration with an NGO called Conservation International, and they're a very they're not an advocacy organization, they're an action organization, and they're very data driven. And their expertise is in natural solutions for environmental sustainability, and they have a great deal of global reach and expertise in using natural solutions, which includes getting carbon out of the air. So interestingly, a paper was published very recently that shows that certain kind of plants are taking more CO2 out of the atmosphere as the carbon dioxide concentration in the atmosphere is going up. So actually the plants are doing their part to try to help this problem. But yes, we and others are pursuing these solutions because actually we are going to have to go negative carbon in a big way. So I think in our cities we need to be getting as much trees and grass growing in our cities as possible, both for adaptation issues, so heat mitigation in the summer, as well as carbon dioxide uptake. So yes, absolutely have to do that, and we're working on it.
There is also the balcony if there's any questions upstairs.
Oh, okay.
Yes, we have one up here.
Hi, from the balcony. My name is Brock.
I didn't even see you guys up
I'm a
there.
former IIT student here. My question is regarding what do you think is ultimately going to be the tipping point that gets people to take this seriously? It's something that I've thought about for a long time, and it's hard for me to really see the level of urgency in average people. And I mean, the one thing as context that I would say is it seems to be this horrific smog in China has seemed to be a tipping point for them in terms of a way that they can no longer deal, or they have to deal with it. So I'm just curious on your thoughts about that.
Yeah, so actually, public opinion in this country with regard to climate change is moving very rapidly. okay? I mean, and the droughts and then the floods in Texas have helped. Sandy has helped. And, you know, it's a shame that extreme weather events are, you know, so effective in mobilizing, but it takes a crisis, really, to get people's attention. So I worry less about public opinion than I worry about political will. And so that's where I think the work has to be done. And by the way, I spend a day a week, at least in Washington, trying to work on that. Yes.
Yeah, thank you very much. I think that the elephant in the room is the amount of population we have. We never touch that. But if you exceed the capacity of the Earth to carry the population that we have, then nothing we can do to destroy everything, the forest, the animals, the air, everything else. And it seems like we refuse to look at that. And I have been in many conferences, and boy, that's not mentioned. We are really polluting the sea with 90,000 tons of plastic entering every day that have chemical and biological consequences on the sea. How do you think that we will change that attitude?
Yeah, well, it's, you know, there will be a major issues with providing resources, so a major competition for the resources that are available. For example, the Earth basically has a fixed amount of fresh water, okay? And more people are competing for that fixed amount of fresh water. Growing enough food for the world's growing population is going to be a major challenge, and so I think issues like that, as they come to play, are really what's going to drive the population issue. I don't just, you know, if you know, a big part of the issue that we have is a population issue. You know, we have more people, and those people want a higher standard of living, and so they need energy to have it. And in, you know, the United States and Western Europe, we had relatively cheap sources of energy. It was driven by fossil fuels. It built our economies into the favorable state that they are. And these other countries, they want those same benefits. But, you know, at the time when all of this started, I think people didn't realize the consequences of what was happening. And so, you know, frankly, all of us were part of the problem, and all of us now need to be a part of the solution. About one more here.
Hi, I'm Simone. I'm a student here in IIT in the Sustainability Management program. So you said that we need policies to allow technology to be deployed. So what is your message for the corporations to contribute for this process?
So we need
policies. We need policies to allow technologies to be deployed. So my question is, in terms of what is your message for the corporations for them to contribute more, for not only the government, how does the corporations can be more actively part of this process?
Okay, so we could solve this in, so the way to solve it is if you have too much of something that you don't want and you want to have less of it, you price it, okay? So if we had a price on carbon, and if it was a realistic price on carbon that really addressed the social harm that carbon does, that would provide the incentive to accelerate the clean energy solutions. So if we had either a cap and trade or a carbon tax, you would see a big change very quickly. How about this guy right down here?
Oh, can you hear me? Sorry. So I just had one quick question because I noticed like you were talking about the different forms of alternative energy, but I was just wondering what your thoughts on wind and hydroelectric energy is. And then the other question I had was just on like how you're talking about when it comes to continuing using fossil fuels. What about like the countries that have actually tried to like push away from it, such like I think like Portugal and like Costa Rica have both done like massive things where they've used a combination to actually eliminate using fossil fuels for like so many hours out of a week or a day or something like that.
Yeah. So, okay, so to say, hydro. So in New England, we're teaming with Quebec, which has been very aggressive about decarbonizing their energy system. And so where you have the ability to use hydro, great. With wind, there's been some opposition. The Cape Wind offshore, was basically killed by lawsuits. But deeper water wind actually has, there's actually a deep water wind project off Block Island which is off the coast of Rhode Island. It's actually not that far, and it has huge community support, and so. So there will be more wind in areas that are particularly windy. We were, touring the Energy Lab at ITT, and there are places in this country where wind is extremely favorable and ought to be deployed. So sure. And then you were talking about countries where there's some mix of fossils. So I'm a huge fan of carbon capture. I think I wish we didn't need to worry about carbon capture because we would stop burning fossil fuels. But the fact is, we can't stop burning fossil fuels for a lot of things right now. And one particular area is like heavy industry. Okay, heavy trucks and construction equipment. But there are actually designs going on. Actually, one of them is by the Saudi Arabian oil company, Saudi Aramco, actually has come up with a portable carbon capture device that you could build into a single vehicle. And then you got to get rid of the carbon from it, so you need a place to do that. But when you have large trucks and construction equipment, those tend to be centralized, and so so that's one of the ways that we're that people are thinking about trying to mitigate fossil fuel use. The airline industry is another area where we need to use fossil fuels, and the airline industry has they've been talking about switching over to biofuels, and that'll solve all their problems, but biofuels are not going to solve all their problems. And so they've been thinking about a carbon tax that is, on the order of 40 cents a ton, which, is a couple of order of magnitudes below what the true cost is. We don't know exactly what the true cost is, but it's at least a couple of orders of magnitudes greater. And so, the aviation industry, I think, is an area that's really ripe for, looking on pricing carbon at a fair amount, and it's a global industry. So it would really demonstrate a lot that we could take steps to solve this problem that are kind of regulatory based. So I think we probably should end pretty soon here because there are people starting to leave and go other places, but also I said we should wrap this up probably pretty soon because there are some people wrapping up, but sure, yeah.
If we have to do carbon capture and most of the earth is water, seems to me the one very key part of the solution will have to be various marine creatures building shells of the carbonates in the ocean and coral reefs and oyster beds and little lobsters running around. And how does this, what's the prospect for increased absorption of carbon in marine shells?
So it's a pretty slow process, actually, and so I think storing carbon underground is probably a more favorable option, but also taking that carbon and using it for something so if you have a quantity, I mean, economics tells you should figure out something to, like turn your garbage into a product, right? So thinking about how to use that for something, and there are some thoughts going into how it can be used for building materials and things like that that are being explored.